Now we are facing a very practical problem. So what if we want to use more features into the linear model? So previously we just include one model, one feature. So if we have, like in this example, we have three features: size, the built year of the house, and the location to predict the price. Then apparently we need more parameters, right? We still need to keep the intercept, the theta 0, and theta 1 is for size. So now we have year, so we'll assign a new parameter for year, which is theta 2. And the third parameter, the fourth parameter, theta 3 for location. And as we are still using linear model, so we simply use theta 0 plus theta 1 times x1 plus theta 2 times x2 plus theta 3 times x3 as a linear combination to make predictions of the outcome price of the house price. So this is the so-called multiple linear regression models. So returning back to the mind map of machine learning models, previously we only have theta 0 and theta 1 in the red square, in the red box here. So now we include and we place theta 0 and theta 1 as a column vector. So now it's more apparent that if we include multiple features, include n features, so we will have n plus 1 parameters in total, and these n plus 1 features is a very long feature vectors, actually a parameter vectors here from theta 0 to theta n. So now we're gonna use this parameter as the models to make predictions. Actually, we need to first train those models, train those parameters. So we now need to use a very powerful tool, which is matrix representations of the parameters. So to summarize a bit, we set up the goal here, right? The goal is to map the feature vector to y, and the function looks like this way: a linear prediction, a linear function, and the predicted value is basically the similar form, right? And the cost function, it remains the same. We use the mean square errors to be the cost function. But the difference is that the cost function is much longer, right? We need to use yi minus y hat, and y hat is this computed in this way. Okay, so that's why we have got a long cost function. So because this long cost function, we've got a long vector of our parameters. It's not convenient to expand these such a long expressions to make to solve all the linear equations. So we will need to use a matrix to represent all the parameters and the data as well. Okay, so first of all, data. Okay, we use a matrix in m rows, okay, and n plus 1 columns. So the m rows, they are m examples. We have m data points in the training data, and we have n plus 1 columns because we have n plus 1 parameters. We have one intercept parameters theta 0 and the n other parameters corresponding to the n features. Okay? And also the y is also into a n by 1 matrix, which is it's a column vector. It has m rows, but just 1 columns. Okay, so that's our data. Okay, so one thing you should notice is that all the training instances, they are placed into rows. So that first row is the first data points, right? The second row is the second data point. The last row is the mth data points, and they correspond to the each rows in the y. So next, we also use matrix representation for the model parameters too. We have n+1 models, n+1 parameters, so we put it into a n+1 row by 1 column. Basically, it's a long column vector like this. Okay, so here let's continue. We want to make predictions, and the prediction equations we have, which we have just shown in the 2 slides ago, it can also be represented by a matrix multiplication. Okay, all the predicted values y hats is also a n by 1 column vector, and that column vector is the results of multiplying the data matrix, which is n by n+1, with the parameter column vector, which is n+1 by 1. Okay, so applying the rules of matrix multiplication, we need to check the we just need to check the dimensions if they are correct, right? In order to multiply these two matrices, we need to make sure that the dimensions here are the same value. They should match, right? And the resulting matrix has the dimension as m here and the 1 here, right? So that is basically a very neat representation of the how we make predictions. All right, that is the y hat we have. It's in bold, so it's also a vector. Okay, let's continue with the definition of cost functions. Okay, now we need to basically define the cost function also in terms of matrices. All right, so now it's a bit tricky, as it requires some imagination in terms of how to do vector dot product. So remember the dimensions for the y hats. It's n by 1 column vector, and the y, it's also n by 1. So the difference, but if we subtract y hat from y, the result is also a n by 1 column vector. So here, the transpose on the n by 1 column vector will result in a 1 by m vector. And here, y minus y hat is still m by 1 vector. So it's the transpose here is basically flip the column vector into a row vector. We just let it lay down, right? Lay that vector down. And the results of multiplying this row vector and the column vector is a single number, right? It's the way how we conduct the dot product. Okay, so this will result in a number which is our cost. Okay, and also we will need to use this 1/2m as a normalization terms. Next, if we apply the equation of y hat is x times theta. If we substitute that equation into the into the expression of the cost function, right? Then we'll get this term, this expression. So the cost function is this matrix transposed times the same matrix here. So the y hat becomes it's better this way. So the y hat becomes x times theta. And then we can apply the rules of matrix calculus, right? So the transpose can move into the parenthesis, y hat get transferred, y get transferred, and x times theta also get transferred. And then we can apply the similar arithmetic rules by removing this parenthesis, which we've got a extended terms here. So that's the form of cost function in the matrix form. Okay, so observing that these two terms here, they are actually the same term, then we can combine them with the coefficient 2 here. So, and we also make the also make the transpose symbols into the each term into the products, which will result given the by applying the rule of transpose, we need to switch around the theta and x, and same here, theta transpose and the x transpose. So this is a very typical quadratic-like function with respect to theta, but only used in the matrix form. Okay. So what's left is that we need to compute the derivatives of the cost function. Right? We also need to keep in mind that the cost function is a function with respect to the theta. And now theta is a parameter. It is not a single variable, but the same rules will apply to vectors as compared to single variables. Okay, and we need to compute the derivative of the function with respect to theta. So by using the rules of computing the derivative with respect to vector, it's pretty similar to the way how we compute derivatives with respect to single variables. So we can put the theta here as a partial derivative, right? So because the y transpose times y is a constant relative to with respect to theta, so this term is gone, and here we need to compute the two partial derivatives, and what's left is basically the constant coefficients 2 times x transpose times y, right, in this term, and 2 times x transpose times x times theta. Okay, so this is a higher order term of theta. It's more like it's a very like the quadratic term in the single variable case. Okay, so we let the derivatives to be 0 in order to solve it. Okay, so these are quite, as I mentioned, this is a quite analogy to the scalar variables to a single variable. All right, so we can solve it. So this is something we can solve it because further move around the terms in this equation will result in this one, and the theta is simply the reverse of the x transpose times x transpose times y. Okay, and x and y, they are merely data. Remember, x is the whole data sets with m rows and n+1 columns, and y is all the labels with m rows and 1 column. So given the data, we're able to complete the solution to the linear regression model in one shot. Here's the solution we want, right? So this is the what we call normal equation solution to the matrix form linear regression models. So this link is quite useful in terms of how to obtain this solution with more details. Okay, so we'll need to use some knowledge in linear algebra about how to compute the reverse of a matrix. Okay, but we don't need to do that manually. Now all the programming packages allow us to compute the matrix operations very quickly, including NumPy that we will use. Okay, so there are a few tips that will help you understand the whole process more clearly. So first of all, if we want to compute a derivative of a cost function with respect to a vector, okay, a vector instead of just with respect to one number, then this partial derivative is also the same dimension of theta. Say, if the theta is a 3×1 vector, then the derivative of the cost function with respect to theta is also a partial derivative, is also a 3x1 parameter. And each component in that vector is the partial derivative with of j with respect to theta 0, theta 1, and theta n with respect to each component in the vector. So that's one trick that we need to know about. And the second is to check dimensions, right? When we use matrix multiplications, the dimensions must match. Otherwise, if you use Python, you use NumPy, NumPy will return error. It says that these two matrices, they don't have matched dimensions. So in our case, the dimensions of theta is n+1 by 1, and for y it's n by 1, and for x it's n by n+1 by 1, n by n+1. So if we conduct matrix multiplications, we can do the game of matching numbers. Say here we've got X transpose, right? X transpose has the dimension of n+1 by n. It's just a flip around of X. And if we times X transpose with X, which means we need to time this one with this one, right? So the n will be gone, and the result is a n+1 by n+1 big matrix, okay? And we compute the reverse of it. The reverse doesn't change the dimensions of a matrix. And so the results of times this with this will remove the n+1, which will result in a n+1 by n dimensional matrix. And then we further eliminate these two, which results in the n+1 by 1, which is exactly the same form as the theta on the left. So the left and right match. So our equation is no problem in terms of dimensions. So that's some tricks you can use when you design matrix multiplications in your programming language. Okay. So here our mental model can be updated. So now we can think of data as matrices, x and y's, right? And our theta is in such a form is also a combination of those matrices. So we can very quickly get the parameters for linear models given the data and the labels. That's one of the advantage of normal equation method. It's a very straightforward solution. Okay, but also we need to keep in mind that we still need have a very salient issue with the normal equation method, because it's quite fast to compute in one feature with one feature, right? If we just use single linear regression model, but it could be slow when we have a lot of features. So when our n is large, okay, because we need to compute the reverse of a n+1 by n+1 matrix. So when n is large, this step is very computationally expensive. It is not easy to compute a reverse of a large matrix. Okay, so that's why basically we will need other approaches of fitting a linear regression model, and which we will introduce in the next video, which is about gradient descent method.